Hello, my name is Yusuf Osman, and in this video, Dario, Brian, Jeremy, and myself are going to be presenting our cooling project for IGEN 430. So, as you may know, climate change has led to global warming and an increase in the frequency and intensity of extreme weather events and disasters, and this is expected to continue to increase in the future. In fact, according to the latest IPCC report, extreme weather event frequency has doubled since 1980 and is expected to at least double again under different 1.5 or 2 degree heating scenarios. Our team is going to focus particularly on mitigating the impacts of heat waves that have been endangering human lives in recent summer seasons. These heat waves have been a cause for global concern and have directly caused droughts and endangered ocean life, but more critically, they put people's lives in danger, especially the more vulnerable. While accessibility in LDCs is limited, the global demand for air conditioning is skyrocketing due to global warming, and research shows that comfort cooling may represent one of the largest end-use risks to our climate. Using air conditioners to stay cool accounts for nearly 20% of the total electricity used in buildings around the world today, and 10% of total electricity demand according to the International Energy Agency. This significant issue is regarded by experts as a critical blind spot in today's energy debates. The impact of residential air conditioners alone is set to account for a greater than zero point 0.5 degrees Celsius increase in global temperatures by the year 2100. This further proves that a low cost and sustainable design for air cooler is a necessity and not a luxury. So for our initial user needs and constraints, we determined the objective to be a device that creates a cool microclimate for those who need instant relief from heat waves to prevent short or long-term physical damage from hot, dry, or humid air. The need statement is then determined to be a cooling device with low manufacturing, operating, and environmental costs that cools air to ideal temperatures of 17.5 to 28 degrees Celsius and humidity between 25% to 55% during heat waves in both dry and humid weather. These are the conditions that are considered ideal for human comfort. And the users are determined to be people in the least developed countries with hot, humid weather, in places with high wet bulb temperature. Our initial plan then was to achieve these goals by utilizing evaporative cooling in combination with a desiccant system that would remove moisture and allow the system to work in dry and humid conditions as well. However, due to limited resources as well as our own lack of expertise in designing HVAC systems, we decided to transition to an indirect evaporative cooling project that would provide a better coefficient of power than traditional evaporative coolers while not contributing HCFCs that further devastate the climate. It's a sustainable compromise that should still provide comfort while not contributing to climate change. This should also achieve all our initial goals, except for having the ability to operate in areas with high humidity. Brian will further explain the design.
Hello everyone, this is Brian, and I will start with an overview of our design. We want to design a cooling system that utilizes indirect evaporative cooling. As seen in the image on the right, indirect evaporative cooling uses latent cooling to reduce the temperature of a secondary airstream. Then the cooled secondary airstream exchanges heat with the primary airstream, lowering the primary airstream's temperature. Finally, the primary airstream goes into the cooling space. We want to use indirect evaporative cooling because compared to refrigerant-based cooling, evaporative cooling is about 50% more energy efficient, and because indirect evaporative cooling delivers less humidity to the cooled space than direct evaporative cooling does. We developed a scaled-down prototype of our design, as the full design specifications are difficult to achieve with our resources. Our project has 3 modules to design: the evaporative cooler, the heat exchanger, and the testbed. The testbed is designed to bring ambient air temperature up to outdoor air temperature specified in our design. Industrial-grade heat lamps are used to heat copper coils to around 60 degrees Celsius. These copper coils heat the air that enters into the testbed and can heat the air from 18 degrees Celsius to 25 degrees Celsius. The fans on the front of the testbed is 5 inches in diameter and pulls air into the testbed at a rate of 0.047 cubic meters per second. The design objectives of the evaporative cooler is to provide about 16 watt of cooling power to the input airstream. As seen in the photo, evaporative pads are placed on 3 sides of a plastic box, covering one airstream inlet each. This maximizes utilization of box surface area for highest cooling power. We form a water cycle through the use of a submersible pump and plastic tubing, pumping water above so water can trickle down the evaporative pads. Finally, we use a draw-through centrifugal fan, which can handle higher pressure differentials than inline fans, to move the air through the resistive evaporative pads and into the heat exchanger. The main design objective of the heat exchanger, as seen in the diagram to the right, is for the evaporative cooler airstream to remove about 13 watt of energy from the supply airstream. The evaporative cooler airstream will be the secondary airstream, while the supply airstream will be the primary airstream. We decided to use a counterflow heat exchanger because we want to minimize the volume of our product, and a counterflow heat exchanger is more effective at smaller sizes than the competitor, a cross-flow heat exchanger. To be more specific, we designed a nested pipe heat exchanger. Our initial idea is to design a helical heat exchanger which has the best volume to surface area ratio, but the design is impossible to manufacture, so we simplified the design to straight pipes. Because the heat exchanger handles fluids, interfaces between different parts, such as the space between the outer PVC piping and the polyethylene plate at the center of the image on the left side, or between the polyethylene plate and the 7 copper pipes, are sealed off using silicone sealant, which is sufficient to prevent air leakage. We rely on SolidWorks and other software to present details on the heat exchanger, as the end product must be sealed and is therefore difficult to physically demonstrate. In designing the heat exchanger, we made some assumptions to how it functions. We assume that each of the 7 copper pipes have the same temperature profile, and also an uniform airflow profile that is the same for each pipe, so that each pipe contributes evenly to the heat exchanger capacity.
My name is Jeremy, and I'm going to be analyzing our design. First, I'm going to take you through a completed version of the project and explain how all the parts work together. Then I will discuss how far into the physical prototyping process we got and our aerodynamic analysis. Finally, I will touch on the breakdown of our project's budget. This diagram shows how all parts of the project work together. Air enters the system through the test bed, where it is heated to operating conditions. The warm air is then split into 4 channels. 3 enter the evaporative cooling unit and 1 enters the heat exchanger. The reason 3 inlets are used on the evaporative cooler is to employ the use of 3 different evaporative cooling pads. This provides the maximum amount of air cooling from the evaporative cooler's geometry. The air cooled in the evaporative cooler is then passed to the first inlet of the heat exchanger. Once in the heat exchanger, this cold stream of air cools a warm stream of air coming directly from the test bed. Once cooled, the air from the test bed is used to lower the temperature in the cooled space. The reasoning for this method is that it results in the air cooling the room being significantly less humid than the air coming from the evaporative cooler. Even though the air coming from the evaporative cooler has a lower temperature than that coming from the heat exchanger, it is also significantly more humid. By using the heat exchanger to cool air indirectly, the outlet air is not only cool but significantly less humid. This is arguably the most important part of our project, as humidity, or relative lack thereof, is identified as a major factor in human comfort. Therefore, this method results in a far more comfortable cooling experience than the traditional evaporative cooler could provide. Here, you see how far our group got into the physical construction of our prototype. As you know, COVID-19 abruptly ended our ability to develop and test our project about 3 weeks ago. Despite that, both the heat exchanger and evaporative cooler are fully complete. The test bed and cooled room are both a day away from being complete, and if a few items were still needed for formal testing, namely Arduino controller as well as temperature and humidity sensors. As well, the test bed still needed to be properly sealed. It is feasible, though, to say that our project would have been ready for testing within less than a week of work. Since we were unable to perform physical testing on our project, our group chose to perform an in-depth aerodynamic analysis to evaluate our design. We started by analyzing the heat exchanger, which we'll notice is not pictured here. This is because our analysis, being theoretical of course, agreed 100% with the calculations that were carried out in the beginning of this endeavor. In the testbed, it is clear that the number of heating coils paired with the length of the testbed and the relatively slow inlet velocity made it hard for flow to reach the outlet. This is shown on the diagrams on the top left by the significant drop-off of number of flow lines towards the back end of the system. Furthermore, the analysis indicates that a significant amount of air escapes out the holes that house the heating lamps, an issue that would easily be rectifiable in testing. Should development on the testbed ever continue, it would be advisable to raise up the heating lamps and seal the base to prevent this type of air leakage. Furthermore, it would also be advisable to use a slightly stronger fan to push a slightly larger airflow velocity in the front of the system. When analyzing the evaporative cooler, assumptions needed to be made in order to simulate the role of the evaporative cooling pads. Since these pads are essentially large porous walls, we made the decision to model them as walls with the maximum number of holes we could reasonably use without crashing SOLIDWORKS. As well, SOLIDWORKS would only allow for accurate modeling of the airflow one direction at a time. The solution to this was to analyze flow from each inlet direction separately and make inferences around the outlet about how the flows would interact with one another. Since each direction of flow presented a heavily similar flow pattern, only one dimension of flow is shown here for simplicity of understanding. Two major problems in the evaporative cooler became immediately apparent. Firstly, a large amount of air was escaping over the top of the evaporative cooling pads, as shown in the picture in the bottom right. To remedy this for physical prototyping, a sealant would need to be used to force air to pass through the evaporative cooler and not around it. Secondly, air entering the system was not spreading out to interact with the entire evaporative cooling pad, significantly lowering the efficiency of the system. This phenomena can be seen in the photo on the bottom left, where the air entering the system seems to pass straight through the evaporative pad with little resistance. While this issue may be related to assumptions made in the SOLIDWORKS designs of the evaporative pad, a physical prototype could also remedy this problem by having longer inlets that progressively widen into the side of the evaporative cooling pad. This is our budget breakdown. You can see that we have used 92% of our budget, and the majority has been spent on structural parts. This includes the various pieces of wood, plastic, and metal needed for construction of the physical prototype. A considerable amount of money was also spent on electrical components, namely fans and a water pump. Finally, the smallest amount was spent on the evaporative cooling pads. Although the majority of the components needed to complete the project have been purchased, the items we still needed would almost certainly have put the project over the IGEN budget. However, had we been able to continue, we would have been able to get a large portion of that overage refunded through grants from Sustain Engineering. Next, Dario is going to talk about what we didn't get to finish and conclude our presentation.
Thank you, Jeremy. Now I will talk about the heat exchanger analysis. We can determine the heat exchanger efficiency by monitoring the air state before and after entering. By recording the temperature and relative humidity of the air, we can find additional properties such as enthalpy, which helps determine the amount of energy the two air streams exchange. Then, the heat exchanger efficiency can be found as a ratio of energy lost or gained. We can also compare the air states we got to theoretical outcomes and identify if the prototype meets design criteria. One major limitation of our design, however, is the poor heat transfer coefficient between air streams. U is related to the convective thermal conductivity of the material or medium. This is lower for air than metals, and therefore a lot more heat transfer area must be used to transfer heat at the same rate as heat exchangers operating with other, more efficient fluids. Moving on, ideally, if time could have been spent finishing the project, the team would have accomplished a final build of the proposed design, taking into account the scope and objectives of the project. An integration of all components, meaning the test bed for simulation purposes, the evaporative cooler, and the heat exchanger, with fans circulating air throughout the unit. It will also include simple electronic components like a battery to power the pump, the heat lamps and the fans, and the temperature humidity sensors to assess the efficiency. Finally, a microcontroller which would control all the electrical elements. The team would have ideally met stakeholder needs and specifications and ultimately finalize the project with an air conditioning unit capable of cooling air from 25 degrees C to 22 degrees C through the principle of evaporative cooling. For the disposal of the project, the team made sure that every individual component was made from parts that could be reused or recycled easily, with the exception, however, of the heat exchanger, which needed specific materials to achieve a certain desired temperature change. As we can see, the evaporative cooler was mostly made of plastic and cardboard, while the testbed was made of wood. The heat lamps and the pump fan and all other electrical components like the microcontrollers and the temperature humidity sensors can all be easily repurposed. Some plastic tubing where holes were poked would have to go to waste, but other plastic tubing where no holes were poked could be recycled or repurposed. Finally, the team theoretically tested the efficiency and effectiveness of the design using all the resources available. Preliminary calculations were made to determine the ability to cool air, and from these calculations, a prototype was partially built before physical distancing took effect. For this reason, no physical testing was able to be performed, and hence we moved to CFD testing, which Jeremy already mentioned. No further iterations or improvements were able to be made to the final design. So from what we can gather, after assessing the design in its current form and performing some CFD to the final form, it is safe to assume that given appropriate conditions and time constraints, project would have worked as intended to a certain degree. We are unable to objectively conclude, however, if specified target temperatures would have been achieved realistically. Also, the device lacks some supply air humidity control, which can be a comfort dilemma for people during the summer. This is how the project was divided between the group members. Jeremy focused mainly on the testbed building, simulation using CFD, and budgeting. Brian did all the calculations for the engineering problems, verified the designs, and worked mostly on the heat exchanger. Myself and Yusuf, we mostly focused on the evaporative cooler design and integration, while I focused more on SolidWorks and the computer-aided design, and Yusuf managed the team. To conclude, we began with an idea that quickly changed as we shifted our scope and focus. The new project scope led us to building a partial prototype, which was unfinished and untested. So further analysis had to be made using the CAD models designed and the CFD to determine the efficiency and provide some insight. This proved quite inefficient. So if we would have hypothetically finished building the project, the team would have expected the prototype to successfully work to a certain extent. However, the final design proves impractical to scale up since there would be little gain in doing so. Finally, if more time would have been allocated to iterating and improving design based on testing, the team is confident that a higher efficiency could have been achieved, and we could have addressed the humid area ineffectiveness by combining this design with the desiccant technology. Thank you so much for listening, and have a great day.